Good afternoon and welcome to another lecture in MAE 113 Calculus for the Liberal Arts. My name is Richard Kohar and today we'll be covering section 1.2, Limits. Now, I was talking with my supervisor earlier today and it was very interesting because I made the proposition that it's not my job to motivate students, that they should be interested in it already. And I think that I treat calculus in terms of a tool. And, sorry, I was keeping an eye on the chat as well. So I treat calculus as a tool. And we think, we've been looking at previously, we were looking at rates of change. We were looking at velocity, which is like the rate of change in the position over time. And I should probably said, like, why are we interested in rates of change? But, you know, instead of using the royal we, I should probably say why I'm interested in rates of change. And again, it's a tool. It's, you know, it's a hammer, it's a screwdriver. It's only the interest is from the person, not the tool itself. So it's what you're bringing to the tool that ultimately will create something from it. So when I was, for instance, when I was thinking, I know we're stuck inside all day and we also have COVID-19, but I immediately went to online and I saw, you know, I typed a number of cases in Ontario just to see what happens. And I get, you know, interesting headlines. So the first one was CP24, which said that Ontario reports more than 2,600 new cases of COVID-19. Okay, but if you tell somebody or you tell me like 2,600 new cases, okay, is that good? Is that bad? In my mind, I'm already thinking about rates of change. Is this getting better or is this getting worse? And so the next thing, again, people are interested in rates of change because we look over at the next headline at CBC, which says that there's the reporting, there's the number of cases in Ontario, but notice how they also tell us the number of cases continues to fall, meaning that the number of cases is slowing down. So that's interesting for us, right? That hopefully soon the lockdown will be finished here in Ontario. And again, we're not so much interested in, you know, how many cases are there right now. We want to know, is this getting better? Is this getting worse? Is it slowing down? Is it speeding up? So again, I can just jump in quickly to like the Kingston, Frontenac, and Lennox and Eglinton health unit. And this is provided through covid-19.ontario.ca/data. And so we can see that they've plotted it, which is kind of nice. And we can kind of see that over time, you know, it's increasing, but around this point in time, around, you know, January 7th, we actually start to slow down. So let me just jump back to my paper here. So when we're interested in rates of change, we notice that, say, like on January 21st, which is today, we had 627 cases. And again, it's just a number to us. We don't know if it's good or bad. It's just a number. But if we compare, say, like the 17th, which was 620, and we look at the previous day on the 16th, we have 618. We say that that was a change of 2 cases. That was over one day. Now, if we look at a previous time period, say the 17th, on the 16th, there was 421 cases, and the previous day on the 16th, we had 405 cases, which is a change in 16 cases. So in that day, between the 16th and 17th, we increased by 16 cases. But what we can see then is that this change is smaller now. So it looks like, hopefully, that we're actually slowing down. And again, that's what we're interested in, rates of change. Okay, so that just kind of gives you an idea that we are living with rates of change all the time, and we have questions that we are interested in. So sometimes just knowing, data points isn't good enough for us. We have other questions that we want to answer about it. So just so that we don't, make sure that we're making a connection to other topics, because again, we traditionally teach this with like velocity and acceleration, or if we're talking about the geometric interpretation, we're talking about how to find a tangent to a curve. So that was just a little bit of motivation then for this lecture. So we saw in the previous lecture that limits arise when we're trying to find a tangent to a curve. And again, there was kind of that idea that here's a kind of a graph, and I want to get a tangent to this point. And again, it's a line that's touching at just one point to the curve. And so what we did was we need 2 points, and we gradually walk that point closer and closer to this point. And that was the idea of the limit, that we're getting really close to it, we're approaching it, but it never equals it. And in fact, limits are basic to all of calculus. So in this section, we're going to look at the idea of a limit in general and the methods for calculating them. So let's investigate a function. So we're going to investigate this function. So we have this function, and what we can do is let's create a table. Now for this, I'm not going to just write this all out. What is a derivative? Somebody is asking in the chat what a derivative is. And we did that in the previous lecture, which was that the derivative, just pull this out. So you can think of that as the derivative is kind of like a function interpretation for the rate of change if we're thinking about it in terms of the physical Sorry, there we go. So we can think of it as rates of change. We can think of it as the tangent. And then, of course, we did how to calculate it previously with our intuitive idea of going from an average. So we were able to form an average, a delta y over delta x. It's a rate of change. That's the average. We're simplifying this expression so that we're able to eliminate the denominator, the delta x, and we let the delta x go to 0, which gives us that instantaneous rate of change. Okay, so that's what we have so far for our definition of a derivative. We will get to a little bit more of a formal definition, but what we're going to do is I'm going to open up LibreOffice. I posted a video on how to install it, and it's just a suite. It's available for free. It's open source. It's available for Mac OS. It's available for Linux. So again, I wanted to make sure that everyone had opportunity, or it's freely available. So we're going to try. I want to do this function. So it's x minus 3 over x squared minus 4x plus 3. So what we're going to do is we're going to consider it from the, when x is less than 3. And we're also going to look at the other side of x, greater than 3. Okay, so here is our f at x. And what I'm going to do is I'm going to type in 2.5. And we're going to do the function. So it's going to be x minus 3 divided by x squared minus 4 times x plus 3. And so I should have a number. Hopefully that's the correct number. A 0.66 all the way to 7. Okay. So I'll double check that. That looks correct. So we're going to get really close to it. So we can do 2.9. And the nice thing about a spreadsheet is that I can repeat my calculation. Okay. And I can get really, really close to it. Again, I don't want to touch it. Let's see if I can. And okay, so it's getting really, really close to 0.5. So we can approach it from the right-hand side. So I can do like 3.5. And I wonder, nope, I have to repeat the same calculation on this side. Okay. So x minus 3 divided by x squared minus 4 times x plus 3. Okay, so I have 0.4. And right here, maybe I want to get a little bit closer, so like 3.1. So I got 0.47, okay, that's good. 0.01, 0.001. There we go. Okay, that's interesting. Maybe I want to back that off. Part of it is due to rounding errors. So after the precision of this, maybe if I had stretched it a little bit more and, nope, apparently I still hit the runoff. Okay. So you can see that as we're going from the left-hand side, as we're getting closer to 3, that we're approaching 0.5. And if we are approaching it from the right-hand side, we're getting really close to 0.5 as well, 0.49999, and so on and so forth. So now that we've created that table, what we're seeing is that the limit of this function x minus 3 over x squared minus 4x plus 3, as x approaches 3 is equal to 1/2. Okay, so again, we want some shortcuts when we're writing in math. So writing this is quite a long statement. And so what we end up writing instead is we abbreviate limit to just lim. So mathematically, we express this as, so lim, limit, as, and then underneath it we will write x with a little arrow going to 3. And then we have the expression x minus 3 over x squared minus 4x plus 3. And then we'll say is equal to 1/2. So we're not saying that this expression at 3 is equal to 1/2, but we're saying that as we're approaching x equals 3, that it's going to equal 1/2. So number 2, here's page 2. So in general, we write the limit as x approaches some number, say x naught, of f at x equals L. And so then we would just read that as, and we say the limit of f at x as x approaches x naught equals L. Okay? And it's very important that just that expression or that idea of just always approaching it. We're never actually making it equal to. So maybe I should write that out more explicitly so that if we can make the values of f at x arbitrarily close to L, and L is our answer, right? So as close to L as we like, by taking x to be sufficiently close to A, oh, sorry, I meant x naught, but not equal 2x naught. Okay. So here's an example. Maybe, just a second, I wonder if I will be able to show this nicely. The other thing that I wanted to graph of x minus 3 over x, just a second, okay, let me just pop over here. So here's the graph of the function that we were looking at previously over here. So it's approaching 0.5. And so same thing as we're getting close to 3. I wonder if I'm able to zoom in. Oops. Oh, I can. Sweet. The miracle of technology. So I can get really, really close to 3. Can I make it equal to 3? No. It jumps over it. Now, why is that? I'll leave it to you. Let's just make a post-it note of that. So we have this function here, x squared minus 4x plus 3. Now we remember that with the domain, that this bottom half, the denominator, cannot equal 0. So let me see, if I actually did put in that value of 3 into here, that becomes 3 squared, which is 9, minus, I have 4 times 3, which is 12, plus 3. So 9 is 12, so that equals 0. So I can't put that number in it. But if you notice, in the graph, it looks like it's continuous, but it's not. So what does that mean? It's probably our computer is telling us one of those lies, because around there, it can't equal 0. So it means that it has to have a hole. So as we're getting close to that, so we have that kind of smooth line. As we're getting close to 3, there's actually a hole in there. So we can't actually, there's no x for that. Is everyone okay with that? So it's interesting that we can actually kind of approach something and the value not actually be there, but by looking at the kind of behavior around that number, we can actually have a limit. So we're always kind of going back to our intuitive understanding of things. So let's intuitively think about this. I have a limit of a function. I have x squared plus 2x minus 3. So in any of these cases, we should expect to be able to get really close to that 5. And actually, this function is continuous. So we should be able to actually make that equal to it. So if I plug that in, intuitively, I would expect it to be 5 squared plus 2 times 5 minus 3. So it's 25 plus 10 minus 3. 25 plus 10 is 35 minus 3 gives me 32. So that's my intuitive thinking about it. But it'd be nice if we were a bit more precise. Can we come up with some rules? And the answer to that is, of course. So we have some basic properties of limits. Okay, and the first thing we're going to do is we're going to assume that the limits of f and g these exist. So I have two functions. I have f and g, and I'm going to let them approach x naught. So we have a sum rule, which is kind of nice because it's very similar to the idea of just being able to apply it, kind of like distributing a number on it. So what I mean here is I have a limit as x goes to x naught of, so I have f plus g. And what this sum rule says is that I can kind of apply this to each function. Plus the limit as x goes to x naught of g. And of course, then there's a difference rule that you can do. And the way that you would just see that is just by making this function, let's say, negative. So there is a difference, which isn't kind of... I don't think it's explicitly stated in the textbook. And the reason for that is because you can derive that this is kind of like an associated rule with it. So all I've done is I've just changed from a plus to a minus, same thing. So again, it just distributes, which is nice. So if we've done addition, then the next one that we'll do is multiplication. So we can do a product rule. So same idea, a product meaning a product of two functions. So I can have the limit as x goes to x naught of f at x times g of x and so again the same idea of just distributing the limit onto each function. So the limit as x goes to 0 of f at x times the limit of x approaching x naught g of x And of course, then there's an associated quotient rule that you can do. And again, it's just applying it to the top and the bottom. Okay. So I think in the textbook, they give a reciprocal rule. So let's write that one. And reciprocal meaning it's a function of 1 over f at x. So here's the limit of x going to x naught. And that's just equal to just applying the limit to that bottom function. And the last one that we have is a constant function. So we have a constant rule, so the limit as x goes to x naught of some constant c is just c. And don't worry, we're going to do some examples so we can apply the rules. I just need a set to work with. They have an identity function. So if I let the limit as x goes to x naught of just x, then that's equal to x naught. Okay. I think that's enough rules. So maybe if we go back to our, which one did I have here? Let's look at this because I have kind of an intuitive, understanding of this one. It'd be nice if we could apply some rules to make sure that it is in fact 32 for this limit. So if I do that, the first thing that I can do is I will apply the sum rule, because I can just apply it to each term here. So let's do that. Plus the limit as x goes to 5 of 2x minus, no, let's do plus limit of x goes to 5 of minus 3. Okay, so for this one, I don't have a rule that tells me explicitly how to handle this x squared. But I can rewrite that as the limit as x goes to 5 of x times x the next thing that I can do is I can think of this, doing the same idea, I can break that up into two terms. I can think of that as 2 times x. So I can apply the limit to each individual one times 2. And again, this is a product, so I got 2 times x. So the limit of x going to 5, x plus. Now the nice thing about this is that minus 3 is a constant. So with this rule, I can already apply this constant rule right here. So I know that that is minus 3 already. Now again, I have a product here, so I can apply it to this. So I have the limit as x goes to 5, x times the limit as x goes to 5 times x, and plus. So again, I have this 2 here, and using that constant rule, that's equal to 2. Do I have a... Oh yes, I have the identity function right here, right? So there's x. So using the identity function, I can... This one is telling me that if I have x, that is equal to x naught. So in this case, this is 5. So I'll plug 5 into there. And I've already done my rule for that, so that's just minus 3. So we know that this is 10 right there. Oh, and I'm almost done now because I can apply the identity rule here and here. So that becomes 5. And right here is times 5 plus 10 minus 3. And 25 plus 10 minus 3, 35 minus 3, 32. So I have a question. Some people were asking me, why is it just minus 3 and not the limit x goes to 5? So I applied it right here, and I went from here to here. So there's my connection. And what I had done here is I applied the constant rule. So there's a constant rule. Okay, does that explain? Does that answer your question, Cameron? Okay, perfect. Yeah, so again, just as... So what I've done from here to here, I took that x squared and I split that, and kind of this part right here is the product rule. Same thing here, I just kind of split it up here. I took that, same idea. Product rule. And to go from kind of this part right here is just applying, I applied the constant rule, and I also applied the identity function. Because this is a constant here, which was 2, and this was the variable x, so I applied, so this was the constant, and this was identity. And when I got to here, this was identity again. And once I got to this point, it was just routine arithmetic. Okay. So let's just do one more example. In that previous example, there's really nothing to kind of worry about. Like, you could just simply put in 5 into this function and you would get 32 out of it. But that's not where the real power of limits come from. The real power of limits comes from, let's say, where I can't put in that value. So let's do 2 plus delta x squared minus 4, all divided by delta x. So again, I can't plug in 0 into this because that creates a denominator with a 0. We can't handle fractions that have 0 in the denominator. So what we need to do is simplify. So what we can do that is we can expand this out so that I get delta x squared plus 4 delta x plus 4. I have a minus 4, all divided by delta x. So again, I'm still just simplifying. I see that I can cancel out that 4 and the minus 4. So what I'm just left with delta x squared plus 4 delta x. We're almost there, because what we can do is we can factor that out. So I have a delta x plus 4 . Okay, so I'm almost done. Now this is where I can actually apply my rules. What I can do now is, this is a sum, so I can do the limit as delta x goes to 0 of delta x plus the limit as delta x goes to 0 of 4. In this case now, I can actually substitute in this value. So you can think of that as a variable, or you can think of it as a variable like this, our constant rule here. Or sorry, no, actually that's our, let's make sure, it's our identity, right? So again, our delta x is like a variable, so it's not a constant, it's a variable. So we can actually let that approach the fixed value that we want. So this delta x goes to 0. So that's why our identity function plus, and now I have just a constant. So when I let, using our constant rule, that's just equal to the constant itself. So that's just equal to 4. And so we've done that. So using our rules now, we actually have kind of a more rigorous way of calculating things, as opposed to just letting, our delta x go to 0. We actually have now rules to follow for that. Okay. before I sign off, is there any more questions about limits? Of course, we're going to talk a little bit more about this, and we're going to then give a formal definition of a derivative using a limit in next lecture. But yes. I just want to make sure that there's no more questions. I will see you then on Monday. If you do have more questions, we will have office hours from 1 to 3 today. So feel free to drop by with questions from the assignment. Otherwise, enjoy your weekend. Well, at least the weekend for us, because our class is done until Monday. Okay. Take care, everyone.